Hello, everyone. My name is Cheddi Charles. I'll be your host here to make my final presentation on the project on convolutional neural network using TensorFlow on the CIFAR 10 dataset. The name of this course is ADTA 5550, and our professor is Dr. Tuang Nguyen. So in this project here, it demonstrates how convolutional neural network works using a CIFAR dataset. And this project is designed using TensorFlow neural network and not the Keras model from TensorFlow. The first part of the project involves designing solid-based model of a convolutional neural network composed of two hidden layers. The accuracy of this was using the test dataset was measured for every 100 steps of training. Next, these results were compared to the results of the MNIST dataset to check to see the accuracy, whether there was improvement, whether there's a big difference between them, and also to give possible reasons to compare the results. Finally, the model was redesigned to see if there's any improvement in the accuracy for the CIFAR 10 dataset. So come along with me, listen carefully as we go along to explain that project. Now let's talk about this CIFAR dataset. First of all, the dataset is made up of 60,000 images for dimensions 32 by 32, colored images, not grayscale, and each of them was categorized into 10 classes, with each class containing 60,000 images. The dataset was split into train and test data. The train is made up of 50,000 images, and the test data is made up of 10,000, where 1,000 represent each class. So no, 1,000 times 10 gives us 10,000 there. Bear in mind that this data set is colored, so RGB. So we're going to have like 3 channels, as we will explain a bit later in the presentation there. So since this data set is surrounded by, understanding convolutional neural network, which is very specialized in image recognition, I'm just going to do a little conversation on that, talking about the neural network here. First of all, this is just a quick demonstration taken from the source medium. So we have this sort of animal, looks like a zebra, and it's made, let's pretend it's made of a 32 by 32 dimension, the width and the height, and it's colored, so it's not grayscale. So we have a 3-channel where each color RGB. So we have 1 channel for red, 1 channel for green, and 1 channel for blue. So 3-channel images there. So this image, the input is placed, first goes to the first layer, convolutional layer there. And in that first layer is made up of different mini layers, I would say. First of all, we have the filter, and we'll talk more about the filter there, the importance of the filter. And the filter is just take a small window of this image to scan through and glides across and glides down. We'll talk about that in terms of slides. And then we're going to use activation energy, not energy, but function called reload. There are other activation functions there, but one of the most popular ones, reload activation, to sort of get non-linear relationships. And after this, they pass through the activation function. Then we have the pooling layer. And the purpose of the pooling layer is to just extract the main information, the main details. And what the pooling does, it reduces the dimension. So, from a 4 by 4 to maybe 2 by 2 dimension, we just sort of reduce it in half there. So sometimes they are called max pooling, and we have average pooling. So max pooling basically, as the word max comes from maximum. So it basically takes the maximum value within that filter when it does the computation. Um, and then, it will reduce that dimension there. After it reaches the first filter layer, and one thing about convolutional layer, they act in hierarchies. So one of the things is that the first layer or first couple layers will extract those simplistic features, maybe the edges and the corners and so forth, the texture. And as the input goes deeper and deeper into the layers, it sort of pick up the more complex patterns, maybe a face, maybe the object. So as it gets deeper and deeper, it becomes picks up the more complex pattern. So that's a good thing about a convolutional neural network. It's a hierarchical where it goes from simple features and it gets deeper and deeper to more complex features. So as the data input pass from one layer to the next, it goes through the same process. You can increase the number of filters. It's on you, change, experiment. Um, and you can do the reloop, pass through the activation, and then you can do pooling. And the next part, and one of the things about those layers is the main thing is feature extraction. And afterwards, you have to flatten the layer, and then this flattened layer now is where it passed through the fully connected layer, just like the multi-layer perception, fully connected multi-layer perception in terms of the neural network. So you have this there, it goes through, you may do some dense pulling there, and you can do, as you can see there, it is fully connected. And at the last end layer of that, you have um, the one that does the classification. So if there are 10 classes, you're going to have 10 outputs. And basically, one of the function there is softmax. Softmax is sometimes you have the logistic one or the sigmoid function where you have the output is binary. But since it's 10 classes, we're going to use the softmax where it gives you a more of the output is more probability there, distribution, as you can see. So let's just talk a little bit more about the details of the different filters, understanding about the slides and the pooling to get a deeper understanding about the convolutional layer. One of them would be the filter there, and we have the strides. So the thing with the filter, the strides tells you how fast or how slow you move. If you move very fast, like 2 strides, you're going to jump every 2 across until you reach to the end and then you jump down 2. Okay, with that being said, it does affect the output. And later on, you'll see a formula that is related to know what type of output you will get. So that's why you have the strides there. And the strides basically tells the filter how forward to move, how downwards, how fast to move there with the calculation. The next part is the filter. Very important there. We talk about filter. So the filter is just a kernel. Sometimes we call it a kernel or weights, where it's a small matrix of learnable weights where it slides over the data, the section. I remember we talked previously about the slides, so it's how fast it slides. And as it slides there, it does a sort of dot matrix product. And if you look at the example there, you can see like the 9 times the 0 is multiplied and do a weighted sum. And the result will be 16. So you do a weighted sum, and so for every slide movement, you do a dot matrix product there, and you get a weighted sum of it there. So that's the purpose of the filter. And you could have hundreds, those filters. You create your own the number of filters based on maybe knowledge base of it or experience. So you can do that there. So look at a summary here of how everything is related to the input. You have the filter, which is in this case the 2x2 filter. You have the stride to the X direction, stride down. And the next thing is the padding. Now, why padding? Now you see the padding is same. What does that mean? If padding equals same, it means that because how the strides movement is, it can reduce the dimension. So what padding does, it fills the borders with zeros. In that way, it will preserve the dimension. So the same dimension of the input will be the same dimension of the output. Now, sometimes the padding is called valid, where you don't include any zeros. So that is where the dimension can be reduced. So just keep that in mind. If padding equals same, that means the dimensions of the input will be the same dimension as the output in this case here. And right under the slide, we have a formula. And in that formula, you can see the input size minus the filter size plus 2 times the padding, okay? And all divided by the stride. Remember the stride, if you move in ones or in twos, plus 1. And you get the flow integer. And that tells you the output size. So just hope that give you a little idea. As you can see from this diagram, there was padding, so you can see zeros all around the input there. It was a 4x4 input, and if you look at it, the output is still 4x4. So the padding do actually work there. So next here. Now the last aspect of the convolutional neural network is the fully connected one, where after you pass through the convolutional layers or the hidden layers, then you have to flatten those, because the thing with convolutional is that it works very well with spatial data, but when it comes to fully connected, it does not work. So you got to flatten those values there, that matrix, I would say. And then from there, you just go, it works just like an ordinary neural network, dense neural network, where you are fully connected, where each neuron is connected to each and every neuron of the subsequent, of the next new layer, I would say. So that's what happened there. Coming to the end, you have this, you have the function, which is the softmax. We talked about that before, and that tells you what category in terms of probability it was that input or that image was categorized into. So that's a summary of the neural network. So let's get into the actual project where we apply those principles, and you can see for that project here. So for the first project, first design, we have one layer, and the label, you have the batch, the width, the depth. So it was, remember, it was a 32 by 32. So we have 32 by 32, and the 32 here for 40 will be number of filters there. The input shape will be 32 by 32 by 3. Remember 3 because it was colored RGB. If it was grayscale, the input shape will be 32 by 32 by 1. But because it's colored, we got to do 3 channels because it's RGB. So 1 for each. The output shape would be 32 by 32 by 32 because remember we added 32 filters. So that's why, you do 32, 32 by 32, which is the height and the width. And then you have the depth, which is 32 channels because of the number of filters. Then we have the filter size. Remember the little matrix there? We use a 5 by 5. So the shape would be 5 by 5 by 3 because there were 3 channels. And remember there were 32 outputs there. So that's the here. The stride was 1, how fast you move. Padding is the same, so we expect the same output. From the input dimension will be the same as the output. And we apply the activation function layer there afterwards. We do the matrix. So just a little bit of after the ReLU layer, here we have the input shape. Same 32 by 32, same output because remember the padding was the same. So nothing changed here. But then if you look at the pooling, we have a filter. The pooling do have a filter also. We use this method called max pooling. Sometimes there's average pooling where you take the average to get that one value there. But this time we use max pooling. And one of the reasons for max pooling or pooling in general is to just extract the main details and to avoid overfitting. In that way, the model can be more generalized, so it can pick up generalized data and be able to perform well. So we have that there. The shape padding is the same. So remember there was 32 input channels, the shape. And now the output, if you look at the last point there, notice the output becomes 16 by 16. Why? Because from a 2 by 2. So because it's like a little filter goes across, take the maximum value, 2 by 2, it reduces the dimension. So think about it there, 2 by 2, little matrix there, just pass it over and just take the maximum value. So now the final output will be 16 by 16 by 32 because remember the 32 channels. Think of like 32 flips, filters, flips, or pages we got to go through. That's why. Okay. So next one, then we move on to another layer after that. But this time, instead of 32 by 32, remember from one layer to the next subsequent. So the output of one layer becomes the input of the next layer. So that's very important. The output of one layer becomes the input of the next layer. So instead of 32 by 32, we have 16 by 16. And remember the depth was 32. Now the output shape, if you notice here, is 16 by 16 by 64. Why? Because we increase in that layer, instead of having 32 filters, we increase it to 64. So obviously the output number of filters in terms of layers will be 64. So it's going to be a 16 by 16 dimension. And then you got to go through, this has to go through like 64, filters again. So that's why it's the output, the channels, we call it the out channels will be 64. Same filter, 5 by 5, there strides, keep it sort of same as the previous one. Went through the activation layer. And from there, we have no filters. So we have the processing there, no extraction, just processing, just doing the calculations there. And we have the input shape there, 16 by 16 by 64. Then we have finally the pooling layer, again, max pooling. So guess what? It reduces the dimension. So from 16 by 16 there, it reduces to 8 by 8 by 64. Remember, it was 64 channels. So it becomes 8 by 8 now by 64. So notice it sort of reduces. If I go back to the shape here, as you can see, just quickly, you notice here that the size, the dimension is getting very small because of max pooling. You see, it gets from a large dimension in terms of length and width, and it gets smaller and smaller as you go through the different layers, deeper and deeper in the layers because of the max pooling. So that just keep that in mind there. So let's move on here. So, and then here again, we have after the pooling, second layer, then we have the fully connected layer where we flatten, remember? Those layers, now we need to flatten in. So we had a flatten matrix to flatten those outputs from here. Okay, remember it was 68 by 8 by 64, so we got to flatten it now. And that's why the shape is for, and then we have number of filters, we add number of filters there. We had a dropout layer, and the reason why we had well, one of the reasons for the dropout layer is to just extract the main details again. It's one of the things called regularization and also help to reduce overfitting. So maybe those neurons that are not significant, it will drop it to 0. So just take those significant neurons there. So that's why we have the dropout layer. And then we have the final layer. And the final layer, the output is 10. And the reason why 10, because there are 10 classes. So we got to keep that in mind, that not just any number, but the number of classes should match the last number here in the last layer, 10. Because there are 10. So each channel represents a class for those images there. So that's the main structure, architecture of this. And then we move on to get the results. So after we do those things, with the functions, so we're going to test, train the data. We're going to train the data. And after 5,000 steps, we use the test data. And this was the accuracy, somewhere right around 67, 68%. May seems a little bit less compared to the other MNIST dataset, which gives us like 99% accuracy. So we got to talk about why was there such a big difference between those two results. Okay, so this was the results of testing the model here. And this graph here shows the difference between the MNIST dataset and the C410 dataset. So that's something we got to talk about there. What are some of the reasons? Let's think about it. First of all, the MNIST dataset is made up of grayscale and made up of digits from 0 to 9. Just digits 0 to 9. Compared to the C4 data set, made up of objects of animals, planes, different colors, backgrounds. Remember, it was 3-channel compared to the 1-channel. So let's see one of the reasons. What are some of the reasons we can think about for this sort of gap in the accuracy? It was almost perfect in terms of accuracy for the MNIST data set. So let's have two little explanation here. Remember the MNIST degree scale, which have 1 channel compared to the C410 images are colored, which have 3 channels. Yes, 3 channels. And then the MNIST dataset is made up of handwritten digits from 0 to 9. It is much easier to extract and identify those features using MNIST dataset. So, less work for the convolutional neural network. So let's go back here. So I decide to improve it, and these are some of the things I try to do. Increase the number of convolutional layers. Maybe by doing that, I can able to get more complex extraction features. Maybe increase the width of each layer. So maybe increase the filters from 64 to maybe 128, 512. Try this out. And reduce the size of the filter. So instead of 5 by 5, 3 by 3. In that way, let's lower the filter. You're able to extract more information. So maybe that might try. So I did those things here to improve it, and I increased it. And these were the results here. So let's just do a quick little conclusion from doing all those results here. First of all, when I did the first data set, we had 99% from the MNST, 99 accuracy. And compared to the first model of the Seaford 10, which had 68%. When redesigning the model, I realized that the Seaford dataset has a slight improvement now of 72%. Now, there was a lot of trial errors doing these things, doing this for the first time, changing how many layers, changing how many filters, even I try to do batch normalization. Sometimes it improves, sometimes it does not. So I included 2 layers, extra layers, and reduce the filter size just to get a bit of, help it to improve the model. And I just got 72%. And one of the things we need to realize that maybe upon research and reading, you could do data augmentation where you can, before data is input into the model, you can change rotation, you can change the color, um, translation, left, right, different things just to may improve it. You may do regularization, like batch normalization. You can even do that, maybe include more dropout or so layer. That might work. You may even change tweak the hypertuning, maybe the gradients or so. You may do those things. So there are different things you could do, but for now, these were the things I tried to do. I got a slight improvement or even increase the number of steps. It may take long, but increase the number of steps there, but that can do it. But bear in mind that even though you increase the number of layers, that does not mean that you'll get a better result. You always have to avoid overfitting, because if this was the case, you can conclude that more layers means better result, but that's not the case. So it's just have to check to see which is the best fit. You might do different techniques how to do it, but it's a good experience for this project. Just playing around with the different parameters, different functions, and just learning more about it. So it was a good project overall, and I thank you so much for listening to my presentation, and thank you very much.